Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Hello from Perth, Western Australia. My name is Craig Price with Surface Water Solutions. I am excited to be hosting your webinar today on climate change impacts on extreme event hydrology. We have three expert presenters for you today. Excited to bring you also in the background some panelists who will help answer your Q&A questions. Around the world, you'll see this slide here that shows all of the attendees around the world and many more. If we could plot all the people who watch these recordings on YouTube afterwards, it would be solid with attendees, I think, all across the planet. So welcome to everybody attending in all the different time zones that you're attending from. And we're excited to have some engaging content with you today. So with no further ado, let's introduce our presenters. We have got David Curtis from West Consultants, Janice Green from the Bureau, Jason Evans from the University of New South Wales. And then from CSIRO, we have Bryson Bates, Tony Rafter, and Marcus Thatcher. So with all you presenters and panelists coming on here, introduce yourself briefly and let us know where you're coming to us from. And let's start with you, David. You're on the west coast of the U.S., I understand, or is that where you're coming to us from?
West Coast of the United States, correct.
All righty. So in the late afternoon for you. Hi, David. Good to see you. Jason, and again, this reads like if you get into AR&R and just Google AR&R for Australian rainfall and runoff climate change, the author list, we've got some of the authors right here with us today. And in the background, Clinton, feel free to turn on your camera as well. We've got some other experts on with you as well. Clinton, formerly with BOM and now with Tetra Tech. Good to see you on board as well. Jason, tell us where you're coming to us from.
Hi everyone, so I'm coming from Sydney, Australia, at the University of New South Wales.
Excellent, good to see you there. Janice, where are you located?
I'm located in sunny Canberra, coming from the Bureau of Meteorology.
All right, I used to see a big bomb building in Melbourne, but we've got some in Canberra as well. Awesome to see you here. Then let's turn to our CSIRO. Am I pronouncing that right? I always say CSIRO, but let's start with Bryson. So you can tell us where you're at today, and tell me, am I pronouncing that correctly?
I'm from Perth, Western Australia, and yes, you are pronouncing it correctly.
Some people say just say the whole acronym CSIRO, but yes, for those who don't know, that's a Commonwealth department for science, and that's something that actually I'll have Tony. Maybe you go next and tell us exactly what CSIRO stands for those attendees who are attending from around the world who have not heard of it in Australia.
Commonwealth Scientific and Industrial Research Organisation, so a government research agency, and I'm coming from Melbourne in Australia.
Awesome. And Marcus?
Yeah, I'm also from Melbourne, Australia, working at CSIRO.
Excellent. Clinton, where are you coming to us from?
Good morning, everyone. From Sydney, Australia.
Sydney, Australia. Well, good to have you on board. We also have the Australian Water School in the background helping out with your IT questions and to making sure this runs smoothly. So I'll frame up one question, and we'll have just a quick back and forth among the panelists, and then we'll turn straight over to David. One of the reasons we selected this as a topic is that I'm an engineer, and a lot of those attending previous AR&R webinars and other similar topics in the past through the Australian Water School. Again, most are engineers. Many come from a background of trying to implement things from a practical standpoint. I get a lot of scopes of work from different agencies, whether they're from council or from private mining companies, and it'll just say in my scope of work, when I'm bidding on this and I'm saying, I'm going to do this work for you, it'll say one line in there, incorporate climate change. And that baffles me sometimes because I don't know, as a practicing engineer, how long is that going to take me? Can I just pull some number and say 18%, I'm going to add this to my flow rate, and yes, I have accounted for climate change, or do I need to do a lot more work? How do I bid on that, and what do I do? So that's one question that I've had. And then lately, especially last week, when Texas was freezing, I hear people on Facebook making comments like, wow, if it's this cold in Texas, then climate change must be going the other direction. So we're all good. And let's try to incorporate some science here and see why is that comment, what can we say to somebody who might make a comment like that? And from a practical standpoint, a third question I'll pose here is, when I see engineers looking at the climate change data and going to the science, and they say, I want to look at the real science, unbiased, I just want to see what's going on. And I'm in an area, I'm building a bridge, and it's in an area where drought is projected to increase. So rainfall is going to decrease, annual rainfall is going down. How come when I incorporate climate change, I need to increase the size of my bridge? How come for this 3-hour duration, I'm getting higher rainfall intensities where over time it's going down? Now, you're going to see a lot of the figures behind this, but I just wanted to throw that out there. We'll hear from the presenters very quickly, but those attending from CSIRO, have you had people ask similar questions to you in the past? So maybe we'll start with Bryson. Has that comment come up to you?
Yes, over many decades. But I think, and here I'm an engineer by background, not a climate scientist, but I think people tend to forget that the climate system is highly nonlinear and very complex. And when you speak of global warming and you start thinking about melting ice sheets, particularly in places like Greenland, and the impact of that extra fresh water on what's called the Atlantic overturning circulation and what impact that has on the Gulf Stream. In fact, when you think about it, it means the weather might eventually get colder because the slowing down the circulation, overturning circulation slows down the Gulf Stream, so you don't get that warm water coming up the coast anymore.
Yeah.
So you can actually get cold weather, but I better hand over to the climate scientists before I go much further.
Yeah, no, thanks. And that frames things up very well, because those kinds of questions and discussions, we'll see the slides and the science behind that now. And we'll see again also that question as to those, particularly in Australia, as a case study, which I think will be of interest to global attendees as well today. Here's one specific area, one continent, where you'll see some examples of how things globally can affect one part of the continent. And those in Australia who are guided in the water field and the water sector by the Australian Rainfall and Runoff Guidelines have that question now. Okay, I look at the guidelines and we'll see some of these sources. What do I do with these? They're very general, but how can we specifically apply these to our projects? So from the global focus first, David, let's have you come on. I'll turn straight over to you for your presentation. Looking forward to hearing from it. Thanks for coming on board.
Okay, thanks everyone. It's great to be here. I'm going to talk for the next few minutes about climate change. Now, I've changed the slide a little bit, and the title is no longer climate change, it's climates change. It's a simple declarative statement because that's what climates do. They change. And they've done so for a very, very long time. In fact, we know this because we have some extremely reliable documentary evidence that at one point in our Earth's history, the Earth was covered by epic sheets of ice, sometimes kilometers thick. Today, not so much. So obviously something happened between the ice ages and today in the climate system that doesn't support the generation of these ice sheets. So fundamentally, I think we all understand that climate changes. But as an engineer, that's a pretty long time scale for me to worry about. So let's shorten that time scale up a little bit. Let's say look back 1,000 years or so. We don't have any observational systems that go back 1,000 years, but we do have some things that we can use as surrogates, like tree rings. So with the judicious use of tree ring data, we can actually reconstruct annual flow volumes in a river system, in this case, the Sacramento River. Now, this trace of annual volumes dating back 1,000 years is kind of is emblematic of the kind of climate that we have here in California. Kind of lurches back and forth like a drunken sailor on shore leave from extreme wet to extreme dry, with not a lot in between. But even 1,000 years is a scale that's a little hard to kind of imagine and wrap our minds around. So let's kind of shorten it up and look at a trailing 30-year average of those annual volumes. And here you can see this 30-year trailing average varies a lot. And it basically it indicates that in the case of California, a plus or minus 50% change in rainfall coming into the state over, say, a 30, 40, 50, or 100-year period. That's a big change. And the fact that we've seen this change and occurs over 1,000 years indicates that that natural variability is a very strong signal in California and likely in other parts of the country as well, in other parts of the world. One of the surprising things is if you look at the difference in time between some of these peaks and valleys, you can change from an extreme wet period to an extreme dry period in a matter of a few decades. In fact, that transition time is well within the capital budgeting programs of a lot of water infrastructure planning horizons. No one is actually planning for that today. They're still planning for a static climate. Now, in California, we always consider ourselves to be perpetually dry. But if you look at the 2007 peak in our hydroclimate locally and go back 1,000 years, that 2007 peak is in the top 5 wet periods for the last 1,100 years. And when you're in the top of that peak, what direction can you go? Go down. And it looks like we're probably already a decade and a half into our next downturn of a multi-decadal period of dryness before the next wet period comes into play. So this is part of the natural way of things in a lot of areas in the world. One of the shortcomings that we have is our observational record. It covers a very, very short period of time. And in this case, you can see there's a strong upward bias in the direction of water supply in California during that period, which actually severely colors some of our decision making. So on top of this natural signal of change, we've been messing with Mother Nature a little bit by tossing a whole lot of stuff up into the atmosphere that changes the characteristics of our climate. If you look at this spiral diagram of global temperature over the last, since 1850, you can see month by month by month the changes over that period of time. And for the first 80 or 90 years, it was pretty stable. But since around 1940, things appear to be spiraling out of control. So we're clearly messing with Mother Nature, and it's causing some really severe impacts. We can see that in our observed record by examining the rainfall data that we do have. And here's an example of a recently published study in 2019, looking at roughly the eastern part of the United States, anything east of the 100th meridian west, and the rainfall west of the 100th meridian. And the blue lines are basically the trend line for the 10-year storm, and the red lines are the trend for the 100-year type events. Just because we get more 100-year or more 10-year events, we're going to get a lot more, some more change, but the amount of change is actually larger in some cases for the more extreme events. But definitely an upward trend. The problem that we have is that it's really difficult to discriminate between these underlying natural variability trends and the trends that we've added to that from the changes that we're making in our atmosphere. What that means for engineers is we have old existing infrastructure that's been designed under older standards, and then we have to turn around and design new infrastructure based on newer data and projecting out into the future. There's an example of Folsom Dam near where I live. The old structure was designed in it was completed in 1955. After that time, the 5 largest storms in the period of record occurred in the basin, and what they thought was 250-year protection had diminished to about 75-year protection. Hence the need for a new spillway. That new spillway had a big old B in front of it in terms of the construction cost. And so what happens now is that dam owners in particular are looking at their spillways, understanding that they might be undersized, and they're saying, okay, if we need to change, I can write that big check to make the change. But don't come back to me 5 years from now and ask for another check. So we have to get it right the first time. And so that's what engineers are facing. The problem that we have is that we kind of see either anecdotally or looking at the actual data that we are changing the weather patterns. We're changing the rainfall patterns. We're seeing more extremes. We're seeing things like what Trey mentioned earlier about the possibility of having less rainfall on an annual basis, but the individual storm characteristics change in a different direction. And the puzzle that we are kind of dealing with right now is that the temperature change signal is really, really strong in terms of looking forward into the future. But there's not nearly as much clarity in the direction of the precipitation amounts. One of the tools that we have we can use our climate change or global climate models to give us an indication of what may happen in the future. Now, there's about 50 or 60 models that are used internationally to assess what happens to our climate. Each one has its own characteristics, and I would recommend that if you're going to use climate models in your analyses in the future, take care to look at the characteristics of those models and determine which of these models work best in your area. The models all aren't created equal. Some handle tropical cyclones better, some handle desert areas better. So look at the kind of models and look at the research done for these models and use models that are most appropriate and represent the weather and climate conditions in your area of interest to the best of your ability. Another really big thing to worry about with the models themselves is the actual resolution of the data. And what we're dealing with is, if you look in the upper left, and if we're dealing with 400 kilometer resolution, that's a picture of the United States, and it's a little blurry, and we barely can see that, yeah, there must be some mountains out in the west, but beyond that, we don't have a lot of detail. At 100 kilometer in the upper right, you can see that things get a little bit better. 25 kilometers, you see quite a bit of definition in the mountain range, and then finally at 10 kilometers, you can see quite a bit. These differences just in the topography of the different generations of the models can make a really big difference in the outcomes of the model results. When we used the global climate models, no matter which one we're using, we still have to deal with what's happening on a local scale as engineers. So in the far right, I've got a blue outline of a county, and domain is about 8,000 square kilometers outlined in blue here in Central California. And when we try to actually use the global climate model data, which is fairly coarse resolution compared to the local design problem, we have to somehow downscale that from the global resolution to a local resolution. And then by doing so, and there are a number of techniques to do that, we can get down so that we're looking at maybe 5 or 10 kilometer resolution, or 25 or 50, depending on the types of models we have. That's better than nothing, but it's still not perfect. When we look at the actual data and we downscale the data, we can look at and project it forward, the different time steps and different return periods for these extreme events. And here I've got 3 examples. And what we did in this particular case, to simplify the problem and to kind of mitigate some of the uncertainties and the variability involved between results from different models, different parameters that we're trying to measure, we simply took the ratio between what we observed from 1950 to 2020 and compared that to what the models were telling us from, say, 2020 to end of the 21st century. By looking at the ratios, we kind of mitigate the uncertainty a little bit, but when you look at across all bands, the 1 day, 2 year, 1 day, 100 year, 1 day, 500 year, the median of our distributions are all above 1, which means that we're looking at increasing intensities going forward in time. So that's a clue in which direction that we want to go. And we could use that information, again, to kind of establish these correction factors. So we take our observed results that we did from the standard rainfall analysis, looking at historical gauge data for anywhere 50 to 100 years worth of data, and apply these correction factors going forward. And we see that our correction factors actually increase with increasing return period, say from the 10 to the 100-year event, and then decrease with increasing duration or increasing time step. So in this particular application, we didn't see a lot of spatial variability within the local domain that we were looking at. So we made it spatially constant. We chose a very conservative approach, is late century results, because that's when this infrastructure is supposed to work. And using the high end of the representative concentration pathways for atmospheric gases, and use kind of an ensemble approach and a risk of exceedance approach to choose which correction factor to use. That was just one quick overview of an approach that can be used. There are several out there that are being investigated and researched, and a little trial and error going on in the commercial consulting sector. But the bottom line is that we're still trying to figure it out and still trying to deliver deliverable, actionable intelligence to our decision makers.
Excellent. Well, thanks so much for that presentation. Just wanted to invite everybody who's attending. We've got 500 attending live right now. You're on board with some of the experts in the field. Do take advantage of that. Keep those questions coming. I see a few of them have been answered already, so thanks to the panelists answering those. We do have in the background some of the authors of AR&R, Mark Babister and Monique Rutalik and others who can answer your questions about Australia specifically as well. So keep those questions coming. Thanks for that, David. David will now jump into the background and start answering those questions too. We'll turn over to Jason now. So thanks, Jason. I can see your screen just fine. Over to you.
Okay, thanks, Craig. And thanks, David. That was some really good information you were giving us there. So I'm going to now think about how climate change is affecting the atmosphere and what that means for rainfall to start with. The first thing that we generally think about is really the thermodynamics of the atmosphere. We often refer to the Clausius-Clapeyron equation, and that basically tells us that there's a relationship between temperature of the atmosphere and how much vapor pressure the atmosphere can hold when it's saturated. And it's a nonlinear relationship. You can see it shown over here. And it means that the amount of water at saturation in the atmosphere goes up by something like about 7% per degree Celsius or per Kelvin as the temperature increases. When we have extreme rainfall, the atmosphere is generally saturated or very close to saturated. So we can expect that the amount of moisture available for that rainfall is going up at something like 7% per Kelvin. And that's a really fundamental thermodynamical property of the atmosphere. But of course, as we heat the atmosphere, that's not the only thing that changes. We also have to think about things like changes in the vertical lapse rate of the atmosphere. So how the temperature is changing with height in the atmosphere. And that can change in complicated ways. But if we take sort of two examples here, if we have an increase in the temperature, but the moisture is staying the same in the atmosphere, then essentially what that does is it forces our cloud base heights to go up higher in the atmosphere, which essentially lowers our chance of rain, right? It's a bit harder to make the clouds form to start with. On the other hand, if both go up together, the temperature and the moisture both go up together, then that actually lowers our cloud bases, so which makes it a bit easier to form the clouds and gives us a bit of a higher chance of rain. Now, these two situations, this first one is kind of indicative of what we have in dry periods, right? We have low levels of moisture in the atmosphere, but if our temperatures go up with climate change and our moisture levels stay low, then in fact, we get a situation like this top one, where our cloud bases go up in the atmosphere and it lowers our chance of rain. On the other hand, this lower example is what we might expect during wet periods. When our atmosphere is close to saturation anyway, what we end up having is cloud bases getting lower. This starts to help us understand why we have situations where we can get more rain in wet periods, but then have longer dry periods in between, because both of these things happen when we warm our atmosphere because of the changes in height in the atmosphere. We also have changes in the amount of condensation buoyancy we get inside clouds. Okay, so as we condense the water vapor in clouds, condense into raindrops, we're releasing heat, which increases the buoyancy of the air in the cloud, and that will increase the updrafts inside the clouds. So for systems that are near saturation, higher temperature means we have more moisture because of the Clausius-Clapeyron relationship. So that means once we form these clouds, inside the clouds, we can condense more moisture out, give the cloud more buoyancy, so we produce stronger updrafts, we get deeper convection, and that can give us more rain as well. Okay, so this is another thing that happens in the atmosphere as we're warming it. And then we can also look at much larger scales in the atmosphere and look at the global circulation that's happening. Here we're looking at vertical cross sections of the global atmosphere from a pole to the equator. And we're really, in the atmosphere in general, this circulation is dominated by this tropical driven Hadley cell circulation. And then we have these, what's often called the Farrell cell circulation next to that, and then a polar cell near the pole. Now, one of the things we see with climate change is the strengthening of this tropical circulation, so this Hadley cell, which often leads to an expansion poleward of the Hadley cell, and that shifts these other cells poleward and moves this main storm tracks in the mid-latitudes towards the pole. So if you can just make out this line here, here we have a situation where this part of this area here is actually in the storm track at this time, But then as we warm the atmosphere and increase the tropical circulation, we're no longer in the storm track at this location. So these changes in global circulation can have really big impacts on particular locations in the globe. And it's often around the movement of the main mid-latitude storm tracks. That's a really brief look at a few of the main mechanisms that are going to be impacting our rainfall as we warm the atmosphere. And now let's think about what that might mean for different durations of rainfall. So most of the effects I talked about, other than the changes in global circulation, they really act on pretty short timescales. So convection timescales, right? The timescales of actually creating these convective cells in the atmosphere. And you can think of this as broadly anywhere from sort of instantaneous through to maybe an hour, right? So it's sort of these minutes timescales. And they also happen on fairly small space scales. So these convective space scales may be on the order of hundreds of meters to kilometer kind of scales. Okay, so if we want models that actually are going to capture these phenomena and how they're changing, we need to be looking at these kind of space and time scales. And as David just mentioned earlier, if you're looking at global climate models, they're quite a long way from these space and time scales. So it's difficult for them to be able to capture all these kind of changes that I've mentioned. Now, for longer duration precipitation, so we're thinking about longer than an hour or so, then we also have to think about the surrounding air masses for the region and whether they're moist or dry. So if we want to have longer duration rainfall extremes, those surrounding air masses need to be moist so that as they converge into the storm, they're bringing lots of moisture with them, which can then be rained out within these convective clouds. Okay, so this is the typical sort of idealized picture that we might have. So we're forming a cloud, we've got buoyant air in here, we've got updrafts driving this up. This low level air has to be replaced by air from around. And in order for this to give us a heavy rainfall event, then this air masses that are converging have to be moist as well, bringing lots of moisture with them. And here we've just got an idealized picture. If we're looking down from above, of course, those air masses can be converging from any direction all around the storm. So for a few hours, you need this kind of thing. So we've got all these things that might change, or many of them enhance convection, where the convection is occurring. But for a few hours, we also need the air a bit further away to also be moist so that when it converges in, it's adding that extra moisture to it as well. So we start thinking about longer timescales, out to 12 hours. Then, of course, there's a much bigger catchment area, if you like, for the storm. So a bigger part of the atmosphere has to be moist because that's the area that the storm is going to have air masses converging into the storm from. So if we want to have heavy precipitation over a longer period, we need to have a bigger area of the atmosphere being close to saturation with lots of moisture in it. If we then think about even longer durations than that, then we need to start thinking about lots of other larger scale aspects of the atmosphere, all these synoptics that are going on, the movement of the high and low pressures, the warm and cold front movement. So it's more than just having moist air around the area we're looking at. It's also how it interacts with all these other synoptic factors going on in the larger area as well. So when we think about these longer duration extremes, we have to be thinking on these sort of synoptic and larger scales, space scales as well. And it turns out that in many cases, on average, when we're looking at these larger things and we have a lot of these phenomena, synoptic scale phenomena interacting and to produce these daily and longer extremes, a lot of the effects kind of average out. And what we actually observe is often quite close to the Clausius-Clapeyron increase with temperature. Okay, so with all those things in mind, I'm going to have a quick look at what some of the climate changes have been projected for Australia, and we'll also have a look at some of these effects elsewhere as well. So here, I'm just comparing what's projected for change in the mean rainfall. This is out towards the end of the 21st century, and compare that to the 99th percentile daily, which in many places is about the heaviest rain day per year in many places. It's not exactly. But what I really want you to show you with this is that, well, first, in the mean, Australia is largely projected to become drier. And these places where you see stippling are the places where the model ensemble agrees that there's significant drying occurring in those locations of Australia. So that's the southwest, the southeast, and the northeast, and some north as well. When we compare what's happening in the mean to what's projected to happen in the extreme here, you see some real differences. So in the northeast and north, the mean and the extreme rainfall are both decreasing. They're going together. But in the southern part of Australia, we see opposite changes where the mean is projected to decrease. We're getting drier, but these extreme rainfall events are projected to increase in magnitude, to become heavier. And this is something that you see in many places around the world in the projections, actually. Not everywhere, but in many places you have declining mean rainfall or no change in mean rainfall, but an increase in these extremes. And here I'm just going to zoom in on the Southeast Australia. Again, here on the left, I'm just showing what's happening to the annual one-day maximum rainfall magnitude. And you can see essentially you're seeing increases everywhere. And here on the right, we're looking at how the number of consecutive dry days is changing at the same time. So you can see significant increases in the length of these dry periods at the same time as we're seeing increases in the magnitude of these heavy rainfall events when they occur. And this is something that we should probably expect. One of the things that I showed earlier, of course, is we expect different changes in the cloud base heights under dry conditions versus wet conditions as we warm the climate, which lead to these opposite changes occurring. If we think about future subdaily extreme precipitation, I want to start by saying that at the moment, we don't really have a robust assessment of changes in subdaily rainfall extremes over Australia at convective scale. So I'm talking about kilometre resolution type scales. We did do some work looking at this over Greater Sydney, and there's lots of caveats around this. But what we did find in this early work is an example here for the 3-hour 1% AEP, we see an increase of about 40% out to 2050. So in that period, we see an increase of about 2 degrees. So that was an increase of about 20% per Kelvin, which is a lot higher than the Clausius-Clapeyron relationship, which would suggest about 7% per Kelvin increase. And it's a lot higher because we have also, as well as Clausius-Clapeyron, we have all these other changes in the atmosphere that also occur, particularly at these shorter timescales. These kind of studies have been done more elsewhere in the world. There's a bunch that have looked at particularly over Europe and North America. So here's some examples that have looked over the USA using convective space and timescales. Here we're focusing just on hourly precipitation results, and what they found in these studies was that the hourly extreme rainfall was increasing, annual extreme rainfall was increasing 50% or more in some regions across the USA. Exceedance probabilities were showing relative increases up to 400%, and that's what we're showing in this figure here from their paper. You can see it's different locations in winter and summer, but in many locations, these relative increases are very high. So this can be thought of as a sort of 1 in 100-year event becoming like a 1 in 25-year event. So occurring much more frequently. And another interesting thing they did in this study is that they found for many storm types, not only are you seeing increases in the precipitation rate, but you're also seeing increases in the area under which is receiving the heavy precipitation. And when you put those things together, you're seeing increases in the storm volume produced by these storms on the order of 80%. Okay, so that's the volume of water that would go towards producing floods. Okay, so it's quite a bit more than just looking at the change in precipitation rate at one point in the storm. The combination of that with the change in storm area becomes really important when we're thinking about the actual volume produced by these storms. Okay, so I'll give a quick summary then. Basically, as the atmosphere warms, there's many atmosphere aspects of the thermodynamics and circulation of the atmosphere that have to change. And this means that climate change will impact precipitation everywhere. There's nowhere that won't be impacted. And some really common changes that we see are, we see increases in daily precipitation extremes. I think David also showed that. Those increases are often around the Clausius-Clapeyron factor of about 7% per degree. We also see increases in length of dry periods between storms, and this, of course, would be very important for thinking about antecedent conditions for when we do get the heavy rainfall. And we often see larger increases in sub-daily precipitation extremes than in daily precipitation extremes. And just with the caveat that this is an ongoing research question, and there's a lot more work to be done to be able to have something really robust around the changes of these short duration extremes.
Excellent. Well, thanks for that, Jason. Just wanted to hit one quick comment here from Franciscus saying that shouldn't we be leaving these decisions on climate change to the hydrological experts like we see here on today, and not to engineers and modelers? And yes, absolutely. This is why we've got Janice on here today helping us with the guidance. I don't want to make these decisions. I don't, this is something that I want others who have studied this for their whole careers to make those decisions. I want to turn to the guidelines and say, all right, tell me what to do as an engineer. I don't want to pick that number. I want somebody else to tell me what that number should be. Let's look into the guidance and see what we've got here for Australia specifically. And again, keep those questions coming in the background, and we'll open it up to a live Q&A session after Janice's presentation. So over to you, Janice. I can see your screen just fine.
And yes, what I want to do is just talk about that these decisions have already been made and are included contained in Australian rainfall runoff. What I want to do first is just talk about the answers to a question that we receive most frequently in the IFD mailbox at the BOM, and that is, do the new design rainfalls incorporate climate change? And I want to answer that in terms of looking at before. So before we started estimating the design rainfalls, the stationarity assessment of observed rainfalls we undertook, and then after, which gets more to the question of how does a hydrologist, how does an engineer include climate change or the possible impacts of climate change in their design rainfalls. And I just want to acknowledge that the work that I'm presenting was undertaken by Dr. Fiona Johnson, who's currently at UNSW, worked for the BOM on this work. And what we wanted to answer right at the beginning of the design rainfall project was, can we use all of the historic data in deriving the new design rainfalls? Or have there been changes so large that only the most recent data should be used? And that's exemplified by this graph, which shows, and it's a little bit dated, but it's what we were looking at back in 2008, is we've had some very obvious dry periods, very obvious wet periods. And as we're all aware, most recently, we've moved back into very dry periods. So in terms of how we looked at this, we did a range of studies, some which we developed ourselves and some which also adopted the approaches that NOAA adopted in the US for when they undertook a similar study. And we used the annual maximum for just over 17,000 daily red stations. Because of the paucity of continuous rainfall stations, we used 58, but they were the long-term continuous rainfall stations. And we undertook the analysis both on a point and a region basis. We looked at trends in annual maxima time series across Australia, and you can see there that we sort of saw what we saw was there were positive trends and there were negative trends, but they were basically both for an hour and for 6 minutes. They were about the same. When we looked at changes to the fetid extreme value distribution, again, we saw whether we were looking at daily data, 1 hour, 6 minute data, 5-year ARI, 100-year ARI, again, we were getting very similar differences in terms of the changes. Looking, as I said, at the regional values rather than just at site, so pooling data, again, what we saw was that we had some significant trends, we had some negative trends and some positive trends. So in conclusion, what we found was there was no significant evidence of non-stationarity in the Australian historic record. Although some individual stations show significant changes over time, when you look at that spatially and you look at it at the regional basis, there was no clear patterns. There's slightly more evidence of change at shorter durations, particularly sub-hourly, But this may just be a reflection of the shorter periods of record for the sub-daily rainfall data, which have a greater impact, more greatly impacted on interdecadal variability. So the decision we were confident in was that we could use the full historical record when deriving design rainfall estimates. And interestingly enough, this is the same conclusions that the US came to when they undertook similar analyses. I just want to make a point here that what we found for this particular study was for the very specific purpose for which the rainfall data were going to be used, and for the durations and probabilities of relevance to design rainfalls. What we found here shouldn't be taken out of context, and it doesn't negate what both David and Jason have been saying in their presentations. So I just need to make that clear so that people don't use these results inappropriately. We move now on to after we've spent our years designing the design rainfalls, how do we incorporate climate change when we're looking at designing infrastructure, and particularly infrastructure which we want to, which has a design life of longer than 20 years. And again, what I'm presenting here is the climate change advice that's provided in Australian rainfall runoff, and which is largely the work of Dr. Bryson Bates and others. And Bryson is part of our Brains Trust today. The climate change advice in ARNR 2019 is very systematic. You can find it in Book 1, Chapter 16. It's a 6-step process. It's a decision tree approach. So it's basically a risk assessment, which enables practitioners to make a decision as to what they should adopt when considering climate change with design rainfalls. The first step is look at the effective life of the structure. Like I said, if the structure is only going to be in service for less than 20 years, then you just use the design rainfalls, which are in Book 2, Chapter 3 of ARNR. If it's longer, you then look at the design standard. Again, if the design standard is the PNF, the probable maximum flood, then you adopt the most up-to-date estimate of the probable maximum precipitation. If it's the design standard isn't in the PNF, then you look at the purpose and nature of the asset, and in particular, the consequences of its failure. So we then move to step 3, and what we're looking at is for what's the consequences of failure. If they're low, again, you just use ARR, the design rainfalls in ARR. If the cost of retrofitting the structure for impacts of climate change is low, again, you use the design rainfalls in ARR. But if it's high, then the next step is to move to a screening analysis. So step 4, you look at what your design AEP is. So if, for example, your design AEP is the 1% or the 1 in 100 AEP, you assess the impacts of the 1 in 200 or the 1 and then the 1 in 500 in order to make a screening analysis of whether, if the the 1 in 100 design rainfall became more extreme and became more like the 1 in 200 or the 1 in 500, what would be the impact of consequences of failure, the cost of retrofitting. If that was going to be high, then you move to the considering the climate change projections in step 5. And that, again, if the climate change projections indicate that the impacts and the residual risk is going to be trivial, you adopt the original design. Now, how do you look at the impacts of climate change? As Cray was saying, fortunately, there's been a lot of work done by experts in this field, and in particular, in this case, CSIRO, who've developed the Climate Futures tool, which looks at, for each of the natural resource management areas or clusters across Australia, and which provides information on projected changes for GCMs, for global climate models, for 14, 20-year periods, and for RCPs, or representative concentration pathways. And this allows you to identify what will be the potential impacts of climate change on the particular region you're working in. If you do find that there's going to be a large impact of climate change, the next step shows that there's a couple of approaches. The first is that the particular area where you're working in may have statutory requirements which specify what you need to adopt if the change due to climate change or the risk due to climate change is large. If not, it becomes an economic analysis. And you're looking at what is the best economic in terms of a benefit cost decision. And this is the response that Bryson gave to one of the questions in the Q&A, that in the end it becomes an economic decision. Now, obviously, the decision tree approach is very, very salutary and very worthwhile going through so that you are making an informed decision. But as hydrologists, as engineers, we do like to have things pre-packaged. And as part of AR&R Data Hub, slightly modified or slightly more detailed versions of the calculations that are undertaken from the Climate Futures tool are included in the AR&R Data Hub. So in addition to getting the information you need, such as the Bureau designed rainfalls and losses and temporal patterns, you also can get the interim climate change factors as part of the assessment. And the purpose of this is it provides you with the lower, or the RCP 4.5, and the upper RCP 8.5 climate change factors, which you can then use to determine the effects of both, and then again make an economic decision as to which to adopt. Thank you.
Excellent. Thanks, Janice. And at this point, let's go ahead and have everybody turn their videos on, or their video feeds and their audio. And I do want to just highlight one quick question. This will be a yes or no question for you, Janice, because the question that you actually answered earlier on the Q&A line had the most upvotes out of any of them. Almost 20 people in our attendees out there said they wanted to know, for the PMP and PMF, if I'm designing for that, do I need to ramp it up? Yes or no?
The short answer is no.
No. I saw that one.
It's a qualified no. As I put into the chat, there's not been a lot of work done. There's a report that you can find on the Bureau webpage of a study that was done in 2009 on climate change and and probable maximum precipitation. Not unexpectedly, what was found was that this study concluded that you can't confirm that PMP estimates will definitely increase under a changing climate. Part of the reason is, we're still trying to get a handle on the impacts of climate change on your normal, if you like, design rainfalls. Until we get that, we have limited opportunity to understand the impacts on that most extreme probable maximum precipitation. But again, in keeping with the advice in AR&R, the advice that's been provided, today, if there are concerns about it, undertake a sensitivity analysis to see what the effects are, awesome. And also to look at the cost of increasing your design or retrofitting your dam, which is never cheap, if there were going to be increases in PMP estimates.
Thanks. And that's, again, this is where with a panel like this, I've seen Janice speak at a number of conferences in the past when we used to do these things live. It's awesome to have these kind of forums where we can all get together. Afterwards, we'd have the chance to have some banter back and forth, and you go up to the presenters and ask your own specific questions. So with this forum, it gives you the chance as attendees to put in, to upvote questions and say, yeah, I'd like to hear more about that. We do want to hear from the speakers, from the panelists who have been frantically answering questions during this entire entire session. And maybe what we'll do first is just have each of you address one question that you've had on the Q&A line, maybe focusing on those that have been upvoted the most. And let's go to our CSIRO attendees first. Let's start with Tony. Is there anything that you've answered there that you want to highlight? Any of the questions that you would like to highlight for the rest of the attendees?
Thanks, Craig. Perhaps I'll start with a question from Mark Lavelle, who's, I'm just answering this in the text at the moment. He's asking about why the ARR guidelines always apply an increase to precipitation, even in areas where the mean precipitation is projected to decrease. He's also asked about regions where maximum precipitation decreases, but in the most recent climate projections for Australia, we found that most regions in Australia have a reduction in mean rainfall, but the daily maximum, the annual maximum daily rainfall goes up all across Australia. So essentially the guidance for an increase in extreme rainfall is based on that kind of information, that even in regions where we expect mean rainfall to go down, extreme rainfall is expected to go up. And that's why the recommendation is to increase the design rainfall everywhere.
Yeah. No, thanks. And that's, again, this is one of these questions for the practitioners. And seeing today's presentation, thanks so much for all those slides. It helps to show that there is a reason behind that, and we can back it up with some of the records and some of the analyses that have been done. And there is some solid science behind those decisions. It's not just a random thing we're picking out of the air. Marcus, over to you. Is there anything you wanted to highlight from the questions that you've answered?
So I'm just struggling to keep up with the questions, but
Exactly.
I'll mention some that I've got to so far. Apologies to the audience for not getting through them as quick. So one of them, a question from, and I apologise for pronouncing your name wrong, Amaran Rinho. We was asking about the best method and software for calculating the effect of climate change on precipitation, extreme rainfall, and its effect on dams. And I guess just in general terms, it's often, I guess we often recommend using a few different methods because it's difficult to have one perfect method, particularly when it comes to climate change or one perfect data set. So often there'll be national climate projection data sets which are being curated so that there's some reasonably good quality. For example, in Australia, there's the Climate Change in Australia website. It's a good source to get some information about that. And that can give you a good idea of some of the range in these predictions, as well as the consistent trends across all the models. And then there was also a question on its effect on dams, and I guess my fellow panelists may have a question on this, but when it gets down to that level of detail, I think I agree with the sentiment before about letting engineers design the dams and things. It's very much a co-design. Like the climate scientists can help, but they can't answer that question by themselves. They can only work with the engineers to combine that information.
Sounds good. I appreciate that answer. Bryson, I've seen you answering a few of these to highlight.
Yes, I think there are a couple of things. One is there seems to be quite a few people who, have very good questions, but I would recommend, in terms of what approaches to use and so on. And look, I really would recommend they have a look at the IPCC Working Group 2 reports to get an idea of what scientific literature is out there on their particular subject, and to dig a little bit deeper and actually read those papers, see what models people are using, how they're approaching their problems and so on. I think that's the only way at the present time that you'll be able to move forward, unless you have access to like a university library and can do some research in terms of finding out what information is out there in general. A lot of people are very focused on the engineering component of the problem. But as Janice mentioned, I responded to someone saying, well, at the end, there's an economic decision to be made in terms of the climate change information you have, what the projected impacts are, how much is it going to cost to protect against those impacts, and what are going to be the benefits. And at the end of the day, there is that's an economic decision. I mean, in terms of engineering, we are responsible for protecting human life, and that's different. But I remember a philosophy once told to me some 20 odd years ago by a fellow engineer that instead of designing things to be fail safe, we should be designing them to fail safely. And I think that's something we should be really starting to think of in terms of incorporating climate change into the designs, because if we start looking at very extreme rainfalls and the possibilities there, we're going to have very expensive infrastructures, and there might be simpler ways of addressing the problem, particularly in terms of staging retrofitting. So if we start out with a design that can be augmented over time and with a reasonable economic cost, then I really do think we start to need to engage with economists who can talk to engineers on this particular type of subject. Because at the end of the day, you're going to have to convince someone that the dollars you intend to spend are going to be worthwhile, and that might even be a politician. Yeah, I think there's a few others that are quite technical, and will take a little bit of effort to to answer properly. But I think the last thing, in terms of the climate change advice in Australian rainfall and runoff, that originally was intended to be an interim document. It's meant to be updated as climate change science progresses. One of the questions was talking about the growth rate being only 5% rather than 7% in the Clausius-Clapeyron relation. Yes, we decided to use 5 because at the time there were some papers around indicating 7 degrees Kelvin. I think that literature has probably grown, and I think at some point that part of AR&R is going to need to be updated. I would also say at the time that equation was the only one really we had any reliability in terms of giving people guidance. I think some of the slides that Jason presented on other factors other than just the thermodynamics are going to be important too, but we're going to need more research in that area before we can give engineers more guidance. So I'll stop there.
Thanks. And as you mentioned, there are a lot of technical questions here. And again, what we'll try to do is compile these, I think, so that those who watch this on YouTube later on don't get deprived of the knowledge base that's gone into answering some of the questions so far. Clinton, if you want to pick one question that you've addressed, I've seen you hit a few of these as someone who's transitioning from the public to private sector. Anything you want to highlight there?
There was just a question from the Pacific, which I think I'll pick up quickly, is that there was a question from someone in Fiji, and it was around should they expect more extremes for rainfall? And I'd really refer them to the Bureau of Meteorology and the Pacific Climate Change site, which I'll send through in the links. To really get detailed information for each of the different island groups across the Pacific. It's hard to give general advice for locations that are so far spread across the ocean. And then there was another question, Jibal from Queensland, around paleoclimatological evidence for past data and past extremes. And I know that's a very active area of research, and so it's really great to do your own literature reviews there, but also if you're, depending on how far back you need to go for your purposes, there is gridded data coverages across Australia from 1900 for rainfall, and there's other data sources within the Bureau to access as well. And I'd really refer everyone to the Climate Change in Australia portal, which is a Bureau CSIRO collaboration for further data there. There's a lot of information and some good links to literature for both past climate and future. Can I ask a curly question of the panelists? I would love there to be a discussion around what happened with Hurricane Harvey and the stalling of the hurricane over Houston. We had a similar circumstance with Dorian, stalled over the Bahamas. And I think the same thing kind of happened with Florence stalling over the Carolinas. So 3 instances of very big synoptic systems and hurricanes stalling or moving very slowly across areas of the US. And I think this is a relevant question for all areas of the globe, especially tropical and subtropical climates, is that could that be something we see more of in the future? And what would that mean for PMF and for engineering? Because that would be a very big impact, I imagine.
All right, and having referenced the U.S., let's maybe have our U.S. Attendee here. Despite my accent, I'm still from the other side of the world here. We've got David coming on, and again, we'll just over to the presenters. I think Janice, we gave you a chance to answer one question. We'll probably close off with this here. Have David, if you answer that question, and then we'll have Jason and have one last one, and then we'll probably need to wrap it up from there. So, David, any response to Clinton's question there?
Yeah, well, I'll take a whack at it. The interesting thing about Harvey relative to the probable maximum precipitation is that kind of the fundamental concept behind the probable maximum precipitation, that number is so large that we'll never ever achieve it. Problem is we did come pretty close in Harvey. And so that's caused a lot of people to completely rethink about, what's it mean to optimize the parameters in a meteorological model to generate the rainfall and in the amounts that occurred there. Interestingly enough, the short-term stuff wasn't all that high, but it was the accumulation by the fact that the hurricane stalled out, and day after day after day, you got really high amounts, and eventually it accumulated high enough that it caused massive, massive problems. And the evidence that I've seen so far in some of the climate change research relative to tropical cyclones is that they're going to slow down. And if that's the case, and they maintain any sort of intensity, then we're going to get larger storm totals.
That makes sense. That's the that's the volume mass balance. You've got to get that's going to increase in volume over time. That just makes sense from that standpoint. So thanks for that explanation. Again, thanks for everyone who's answered these questions so far. Jason, we'll have one. We'll give you the chance to close out with one last question, and then we'll go on to the housekeeping items and the courses and webinars that are available to you in the future. So Jason, anything you've hit that you want to highlight?
Well, I thought I might just add to what David's answered for that Clinton's question there. I think the evidence at the moment is still a little bit unclear about whether we should expect these sort of blocking situations to be more frequent in the future. But what we do see is with generally more energy in the atmosphere, we get more variability. And that means there is probably going to be more opportunities for stalling to occur. Doesn't mean that all hurricanes will stall or anything like that, but there's probably an increased chance that some will. And if they stall in the right place, like Harvey did, so that the inflow is coming over a really warm water body, so you're guaranteed to have saturated inflow that can persist for days, then you'll end up with these kind of situations where you have, really heavy rainfall that just keeps going.
Excellent.
And those warm water bodies are going to be more common in the future.
Yes. Well, thanks for that. It's an honor to be part of this panel or to be amongst the experts here. This is, again, something that some questions that I wanted to get answered for myself. You have got webinars, free webinars, some courses to sign up for. If you see this list here in modeling and, practicing some of these things, putting your model in, and as some of the presenters mentioned, doing a sensitivity analysis. Let's run these models that you can get some help setting up here in our courses, and then let's tweak them and let's see what happens under climate change scenarios. Run these sensitivity analyses. So we've got some exciting webinars coming up as well on water quality, running QGIS for groundwater applications, rating curves, taking stage information and turning it into discharge, and then calibrating your hydraulic model. These are things coming up for practitioners. That's what we put on the agenda. What do you want to hear about? So do fill that out for us. on your survey. Let us know what you want to hear. We've got Australian rainfall and runoff. Those of you from Australia who want to know how to put these things into practice, specifically for Australia, we have got another Australian rainfall and runoff webinar kicking things off, and a series of courses for how you can actually do this yourself, not just the theoretical bits, but let's implement some of these things in some hands-on workshops. So thank you so much to all of the presenters, the panelists, those in the background answering questions. We'll try to get this out to everybody so that you have these resources available to you in the future going forward. So with that, we'll sign off here. Thanks so much to all the attendees. We'll see you next time around. Bye-bye.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.